So if you want to, make use of this multi-layer perceptron or feed-forward neural network or fully connected neural network on images, typically what we tend to do is, of course, the dimension is, let's say, for 10 data set, it is 32 by 32 and the depth is 3. Okay. So I may use these terms channel and depth interchangeably. So one way of applying this MLP on images is to flatten these channels and make it a single vector. Okay. So first we flatten this out. Okay. And if you do that, then the size will be, I just checked, it's 3072 by 1. It's a single vector. Or otherwise we can compute some features. Okay. Traditionally people compute features on these images, and anyhow they finally end up with a vector. We are simply taking the raw pixels as is and flatten that out, and we have vector. And then we feed this as an input to a neural network. Okay, so I have some MLP, multi-layer perceptron, and of course gives me some prediction, the probability distribution if we use softmax function. Okay, so one of the problems or the important bottleneck of using this approach is that if you flatten this out, and if I have in the first hidden layer, we will have lots of weights because each pixel is associated with a unique weight, right? Maybe I say it's x1, x2, x3, all the way up to xn. And for each of these pixels, we associate a weight with it, w1 and w2, w3 for each neuron in the hidden layer, the first hidden layer, right? If my first hidden layer contains some m neurons, then for each of these hidden neuron, I associate a unique weight, and we denote this by some indexes, whatever. Okay. So the question is this necessary? Okay. So one problem that I already talked about in the previous session is when you flatten this out, we lose the spatial relationship between pixels. Okay. So somehow those spatial relationships carries more information. So we want to retain it. And moreover, if we use this as is, then we have to, the parameters in the network simply grows up. Okay. So can we do something, right? In the sense, can we make use of the spatial relationship and also reduce the number of parameters? And, is there a way to do that? So that's where convolutional neural networks pitches in. Okay. So essentially what happens in convolutional neural network is a new concept called as weight sharing is introduced. So let me tell you about that briefly. What is weight sharing in a general setting, not with respect to this problem. What does that mean? Weight sharing, I have, let's say I have some 4 inputs. Okay, again, denote the input within the circle. Don't get confused. It's simply, let's say x2, x3, and x4. Okay. So typically what we do, if I have a single neuron, then we associate a unique weight for each of these elements. But instead, I'm going to use only 2 weights. Let's say I use something called as W1 and W2. Okay. And weight sharing tells that I share W1 with X1 and also with X3. Okay. And W2 looks at X2 as well as X4. Okay. It just, there is no specific reason why I'm connecting it with X1 and X3. But the thing is that I only use 2 weights. Okay. And I share it for the entire inputs. Okay. So this is a straightforward way of reducing number of weights. Okay. We can do that more, in a principled way when we use convolutional neural network, but the concept behind it is this weight sharing approach. Okay. So I'm going to switch the slide. I hope this is clear. So once again, I'm going to use the slides used in the lecture from Professor Mitesh Kapra, because, the presentation is quite neat and also it is quite clear. So anyone can easily grasp the concepts. Okay, I think, oh, sorry. I'm sorry, there was some echo. Okay, is that slide visible at your end?
Yes, sir, we
Yes,
can
sir.
see this module 11.1.
Yeah. See, it is from lecture 11 something. So I'm just using the slide as is. Okay. So the weight sharing brings in this convolution operation. Okay. And if some of you are from signal processing background, even if there is someone, you might have already heard this word convolution. And the way convolution is defined there is quite different. But here it is simply a dot product. Okay. I will explain it. What does that mean? Okay. Let's skip this.
Sir,
So let's,
can I, if I can just ask one question upfront.
yeah.
In stats 2 also, we learned convolution as a statistical concept when you're taking a joint distribution. Is
Yeah.
that linked to this in some way? If you could just help. I mean, if it is, just let us know.
Yeah, so that is exactly what what we do in signal processing as well. So that is a way of computing things quickly. It has some differences, okay, but
Okay.
the sliding operation is there. You can see same sliding stuffs here, but the way the things are multiplied is quite different. We are not doing any flipping, all these stuffs.
Okay. Thank you.
Yeah. Okay, so here you can see that. Why I'm not able to write? Oh, all of a sudden I'm not able to write. If we share it, I'm not able to write that.
Can you also show the previous slide? I think we didn't catch it fully.
Previous slide. No, I haven't used any slide so far. Previously, I shared the whiteboard. I had just written something on the whiteboard. Which slide are you referring to? This I skipped it.
Yeah, fine. If you skipped it intentionally, that's fine. Thank you.
Yeah, I just skipped it intentionally. Yes. Give me a second. I'm not able to write, but in fact, before joining the session, everything was fine. The moment I share it in the Zoom, it prevents me from.
Sir, it might be. So, are you sharing the window?
Yes.
Oh, yeah,
I'm
we can
able
see
to
it.
yeah. Okay. So if you look at here, right? So let's say this is a flat one-dimensional convolution, right? So we have some n elements here, but I'm not going to associate a unique weight for each of these elements. Okay. So we have some set of weights. Okay. In this case, we have 7 elements. And then what we are going to do is in the first step, we are just going to multiply, the input and the weight, that is overlapping areas, right? So X6 is multiplied with W0. So you just focus on 0.01 is multiplied with 1, and this one is multiplied with this element, just overlapping elements. Okay. And it's a dot product. It's a simple dot product. And the result is entered here. So in the next step, what we do is we simply slide the window. Okay. The input, you can think of input as fixed, and we just slide the window. Now, once again, we multiply these overlapping elements. Okay. You can just imagine as if you are placing this the weights on the input on the respective location. Then you just multiply the elements in the weights and the elements in the input element wise. Okay, then sum it up. So you repeat this process. Okay, and of course when we encounter this edge case, right? So we might often append zeros as well if you really wish, because in this case, if you observe my original input, the shape of the original or the size of the original axis, let's say I don't know how many elements are there, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. There are 12 elements, but after this convolution operation, we have only 6. Okay, so there is a reduction in the size. Then if I once again compute, if I have different weights, and then once again I compute the convolution on this output, then it still reduces, the dimension reduces, right? So it keep on reducing. So one thing to retain the dimension as is to append zeros. You can pad zeros along the end, and then you can slide over once again. Okay, so that you can retain the dimension if you want to. So that is called as padding. And here, if you observe, when I move this kernel or weight matrix, you can see we take one pixel at a time, right? Not pixel, one element. We just move the the weight matrix by one element. But you could have also moved the weight matrix by two elements, right? You can simply skip this element. You can place this kernel or weight matrix like this. Okay, that we call it as slide. Okay, so you have two options. One is to keep the dimension of the input and output same. You can add zeros to the input. Okay, in a particular way, you can calculate that how many zeros I need to append. Similarly, you can slide the weight matrix using a concept called stride. Now, let's define that as stride. So if stride is equal to 1, meaning that you slide the weight matrix by one element. If slide is equal to 2, then you slide the weight matrix by two elements, meaning that you skip 1, 2, and then you just start from here. Okay, and there are various reasons why we said stride is equal to 2 that we discuss later, but these two are the arguments that we pass when we do this convolution operation in Pytorch. Okay, so the convolution, once let me write that down. So in Pytorch, you have this nn dot. I'm not able to put dot. So nn dot con 2D or 1D. Okay, so if it is one dimension, you can use con 1D. So there, what are all the arguments it can take, or we need to pass in is there will be 4. I will explain the first 2, and the rest will be the optional arguments are this pad and stride. Okay, so what is padding? We append zeros so that the dimension of the input and output remains same. Striding defines how many elements that the filter has to skip along a particular direction. Okay, so the entire process is extended to 2 dimension. Okay, nothing new in the 2D other than just extending the input to 2 dimension and also the weight matrix to 2 dimension. Okay. Okay, so in image is 2D, and of course it has 3 channels, but it's a 2-dimensional matrix. So we can define a weight, the same concept here. Let's say we have this 3/4 image, and the kernel size is, of course, this is a new terminology we are introducing. Instead of calling it as weight matrix, sometimes people call this as kernel. Okay, sometimes they call it as, from the vision domain, people call it as filters. Okay, but anyhow, we can understand no matter what its name is. So the kernel size is 2/2, the input size is 4/3. So in the first step, we are placing this kernel on top of an input, and then once again we multiply the elements element wise. Again, it's a dot product. Okay, so if you look at this formula, it is simply a dot product. A is multiplied with W, B is multiplied with X, and E is multiplied with Y, and F is with Z. Then we make, we slide this kernel by one step because stride is equal to 1. Once again, we repeat the operation. Okay, and notice that W, X, Y, Z are parameters, and this parameter is shared across the entire input. Okay, so they are focusing internally or intuitively. What we can say is that this particular kernel is looking for, or it will learn some patterns in an input. Okay, it will be sensitive for some patterns in an input. Okay, so we repeat this process.
So sir, basically like what it is doing is kind of a moving average kind of stuff, right?
Yeah.
So basically, like say for example ABEF, okay, like that particular, say for example those 4 pixels, okay,
yes,
ABEF and GHKL, okay, say for example the, like when you are doing this AW plus BX plus EY plus FZ, okay, so this is a moving average. Like,
yes,
like if I think physically, like what it is learning actually in this case?
No, as of now, unless you define the element values. Okay, that I will come to the next. Okay, so now this is an operation. You understand the operation, right? So we are moving the kernel over an image and computing this dot product. Okay, let me move to, so what the kernels are actually mean. So let's say if I put the kernel values, okay, here I'm not learning anything, I'm fixing the values. Okay, the kernel values are 111, all one. Of course, I think if to be an average, it has to be multiplied by 1/9. Right? So to be a moving average, so it should be multiplied by 1/9. So if we fix this value, it is no longer parameter, we are fixing it, and if we carry out some operation, then it
will blur the image.
Yeah, it blurs, and if we fix these values, then it sharpens, and this one detects the edges, right? But of course, there is a mathematical process from which we derived all these values. Okay, it's not some random value, but there we derive the value, but in convolutional neural network, we allow the kernel to learn these values. And here, these are all, we can infer what it does. It actually learns edges. In the previous case, it it actually blurs the image. So it makes sense. But in convolutional neural network, since it is learning the values, I mean, the kernel itself is learning all these values. On the top layer, we can see what it actually learns. Okay, it makes sense. It learns some horizontal line, vertical line, or curve. But when you go deeper, we can't make sense what it actually learns, right? But the key takeaway is that in the kernel, we define some values, and also we randomly initialize it as usual, like as we did in the neural network, right? We randomly initialized all the parameters. Same thing here, the parameters are shared and the parameters are there in the kernel, and we randomly initialize them as well, and it learns it, okay, by back propagation. So everything is learned. Yeah, so the output is, what is the output? That's the question. So the input is an image with 3 channels. Okay, of course, we just displayed two. For time being, you just assume this is this not a color image, it's a grayscale image. Okay. So if it is a grayscale image, then if we slide this kernel over this grayscale image, for each movement, right, for each slide, it produces one number as an output. Once again, it will produce the same image, right? So an input is an image, a 2D image, and the kernel is also 2D. And this kernel slides over this image and produces an output. The output is also a 2D. Okay, it's a feature map. People call it as feature map. Because in relation with the computer vision domain or image processing domain, we feel intuitively the kernels are learning some feature, but we can't make sense of what feature it is. Okay. So this is called as feature map, or sometimes it is also called as activation map. Okay, that also makes sense. So since machine learning is predominantly is a completely interdisciplinary domain, so based on the background, people come up with different names for the same operation. Okay. Okay, so this is the important step. So one kernel slides over an input and produces one feature map. Keep this in mind. And yeah, this is just a summary. If we use color image, right? In color image, we have 3 channels, even though it's a 2D, but we have 3 channels. So there is a depth, right? Now my kernel also becomes 3D. Okay, so the kernel has hidden width and as well as depth. So if the number of, here we have 3 channels, therefore the depth of the kernel is 3. If my input contains 12 channels, then my kernel depth will also be 12. So whatever the input kernel, the depth of the input, then that will be the depth of the kernel as well. Okay, but the entire thing remains same. Once again, it computes the dot product across the depth, not just on spatially to the depth. Okay, then it produces a 2D feature map. Okay, that is the key takeaway. No matter what is the depth of the input, a single kernel always produces a single feature map, okay, or activation map. So obviously the question is, why don't we use multiple kernels? Because each kernel may learn some patterns independently. So we can, use multiple kernels. So yeah, if we use 3 kernels, right, each kernel produces 1 feature map. So the output contains 3 feature map or 3 activation map. So now the output is also, it's a volume, not just a matrix, right? If I use more than 3 kernels, right, then the output will have the same depth. If I use 10 kernels, then the output from the convolution layer is, it has some spatial dimension. Also, the depth is going to be 10. Okay. So all these things might take some time to, understand, but conceptually, I hope you are able to follow it. But once you work with, write some, develop some connet and go through some articles, you will make sense of all of this. Okay. And these are all about padding, all this. I'm just skipping this. You can pad so that you can ensure the input dimension and the output and spatial dimensions remain same, and also stride. Okay, so here you can use this formula as well. And I share this slide later, you can work with all these things. So now I'm skipping ahead to a simple convolutional neural network.
So, sir, like these filters are basically then using some localized information to averaging out. That's all, right?
Yes. It extracts, it always look at things locally.
Right.
Okay. So this is the first, connet that uses gradient based learning. Okay. So there are some precursors, but this is the famous linear one. So here you can see that my input is 32 by 32, and it could be a color image or grayscale, it doesn't matter. I use a kernel. Okay, the first convolution layer, right? In hidden layer, in multi-layer perceptron, we say it's a hidden layer, but in connet, we say it's a convolution layer. So in each convolution layer, you can define as many kernels as you want. So in this convolution layer, you can see that, these are all the information, the filter size, what is the kernel size? The kernel, in the previous case, we defined the kernel as 3 by 3, but not necessarily 3 by 3. It could be 5 by 5, 7 by 7, 11 by 11. Often it is odd valued. Okay. And K is, this P is padding. I hope K stands for number of kernels. Okay. 28 dimension. Yeah, K stands for number of kernels in this particular convolution layer. And S is stride. So if you look at here, my input image is a 2D, 32 by 32, but I use 6 kernels. So each kernel produce 1 feature map. So 6 kernel produce 6 feature maps. I stack them together. Okay. Now the output from the first convolution layer is a volume with spatial dimension of 28 by 28 and the depth of 6. And the next operation people tend to use that they want to reduce the dimension, the spatial dimension. Okay. For that, they use something called as max pooling, which is once again a kernel of size 2 by 2. Okay. So maybe I can give you a simple example. Okay. So initially, the output from the first convolution layer is 28, 28. Of course, we have a depth, okay, depth axis, but let's skip that. Now, in the pooling layer, okay, there are many types of pooling, but if I use max pooling, what it actually does is, if I use a kernel of size 2 by 2, okay, 2 rows, 2 columns, then, okay, there are 4 elements always. Okay, always look at 4 elements. So whatever the maximum in these 4 elements, it will take that as an output. Okay, and then we move this kernel 1 stride or by 2 stride, and then once again we take the maximum of it, and then we take maximum of it. So if you repeat this process, then the spatial dimension shrinks, right? So if I use 2 by 2, then the dimension shrinks to 14 by 14. Remember the max pooling layer, there is no parameter in the max pooling layer. This is a fixed operation, okay? But the depth will never get modified, so it remains same. So 14, 14, and whatever the input depth, it remains as is. So in this case, it is 6. Then you can repeat the process, right? In the next convolution layer, you hear people as define 16 kernels. And of course, all these kernel size, these are all parameters that we need to pass. And once we do that, then it computes this convolution operation. Then it produces, each kernel produces one future map. Since there are 16 kernels, then it produces 16 future map. We stack them together. Now I have the output from the convolution layer 2 is 10, spatially it is 10, 10, and depth is 16. Then you apply max pooling layer, okay? Remember, since we are using max operation in the pooling layer, I call it as max pooling layer. It could be, average pooling, whatever the thing you want, okay? Yeah, so now it becomes 5 by 5, and then depth remains same, 16. So you can think of this entire stuff as future extraction, okay? What all this convolution layer actually does, okay? They are learning some futures. The kernels in these convolution layers are actually learning something. So we call those as futures. And we have to make use of these futures in order to make a final classification, right? So for classification, again, we end up using a fully connected layer, okay? So it's a multi-layer perceptron. So again, this multi-layer perceptron only takes in the vector as an input. So what we need to do is we have to flatten this 5 by 5 by 16 volume into a single vector. It's a very trivial thing, right? So you just stack the elements along the rows for all the channels. Finally, you end up, with a single vector. Then you pass this vector as an input to the neural network, okay? Of course, fully connected layer. And once again, these are all hidden layers. So you can use as many hidden layers as you want, but the output hidden layer is equal to the number of classes in your problem. So it's a digit recognition. I don't know why it is written as alphabet, but it's in fact digit, okay? So there are 10 digits, so there are 10 classes, okay? So we have to use some loss function. Typically it is cross entropy. We compute the loss and then we back propagate. So during the back propagation, the gradients are computed and then we use the same set. So the entire training setup remains same. Only thing is that we replaced multi-layer perceptron with convolution neural network, okay? Then we iteratively learn all the parameters until, we observe a satisfactory performance. This is a very brief intro to CNN. Do you have any questions so far?
So I'm having a query, maybe a very basic query, or when you said initially when you explained us, you said that it will be a dot product, right? While creating the convolution, right?
Yeah.
Yeah. So and when you told us that afterwards it will be stacked. So what actually what operation will be there while stacking it?
Yeah, it is also a dot product along the dimension. See.
Okay.
You can. The element simply overlaps, right? Along the depth as well. So you take a dot product and sum it out.
Okay, thank you.
Yeah.
Sir, okay, how would we know, like the input was 32 into 32, then 28 into 28, 14 into 14, like how can we know the dimensions after applying kernel?
Yeah. So typically we keep the input and output as, the input as square image, but anyhow, the formula is, so whatever the input time, so let's say height, okay? And then whatever the kernel is, so here f is 5, so minus f, plus if you use padding, so I'm using 2p because the padding is done along 2 direction, okay, for height as well as width. And then you divide this by stride and then add 1, okay? So this is the formula, and of course, sometimes when you use this, you will end up with some fractional values. So in such a case, you floor it down. So this is the formula that you have to use. I mean, people in fact use this formula in order to infer all the dimensions, because when you define the network, you need not to, mention all these things because it could be inferred from the given info.
Sir, one question, like say, for example, basically, if I consider that input layer and this pooling layer 2, okay,
Input
like
layer
only
and
between this pooling layer 2, okay.
Okay.
So basically, like if I think in this direction that, okay, this is your input space, okay, and this pooling layer 2 is the output space, okay. You are doing some sort of mapping, okay.
Yes.
So in input, so basically you have a 32 dimensional 32 vectors.
Yes.
Okay. And this is, you are getting into a 5 dimensional 5 vectors. Okay.
Yes.
So you are, so my point is, in input space, say for example, there are 2 patches. Okay. Originally, assume there are 2 patches. Okay.
Okay.
So those 2 patches, if they are, say for example, kind of a distance D. Okay. So similar 2 patches in this 5 by 5 pooling layer, like pooling layer 2, they will be kind of a similar notion of similarity distance similarity.
So you are asking if we look at this input in a space of 32 by 32, actually you have to flatten this out even if you don't. So if my inputs are closer together in the space of 32 by 32, whether the same relationship will be maintained in the across all the layers.
Yes. Because in between you are dropping some of the things, right?
Yes. Yeah, I don't know about the theory. Is there any theoretical proof where it will be maintained always or not? But in practice, I have seen people claim such things, right? So across the network, this relationship has to be maintained. Otherwise, the classification becomes, the thing is, when we reduce the dimension, right? We say it's a future extraction, but when we ultimately we are going to visualize using some sort of dimensionality reduction technique and see whether they are close to each other empirically, right? If you want to do that empirically, that's the thing that we end up doing it. I have seen papers like that, but I have not seen any theoretical claim this will be maintained across the network because of this.
Because if I look at this input space as a graph, right? Input space as a graph, then I do not know, like this input space, how similar that space is in this 5 by 5 space, right? Maybe say, for example, like the density of the nodes, right? And the density of the nodes in 5 by 5 space, like how similar they are, even if I normalize that, how similar they are or dissimilar they are.
Yeah, this is quite involved because we have to define whether we have to use a Euclidean distance to measure the similarity. This sums are somehow involved with manifold learning, but I'm not that much, familiar with.
Like, is there any paper like which deals about this notion, like the thinking image as a graph and then do some kind of a similarity? Because this convolution,
Maybe,
that is one, like I believe that is one weakness. Like maybe wrong.
Okay. Yeah, there are other approaches for this, which is called graph neural networks. You may take a look at that online.
Okay.
So where they consider each pixel as node and they are connected by somehow. So they apply. I mean, the approach is entirely different, but it has some advantage over convolution neural network in terms of some, retaining some variance. It is, people say it's convolutional neural network or translation invariance, because wherever your object in the input image, if you translate it, still neural network should be able to, classify it correctly. So
correct.
So in that aspect, they say it's whether it is equivariance. You can ask so many questions, but if you really want a good depth of comparison, you can compare GNN with CNN.
Okay. Sorry to divert this topic. Okay, thank you.
Sir, I have one question. Sir, from the input, you are giving it to couple of conventional layers, and then you have a pooling layer in the middle. Why are we going for the pooling layers, and what are the params which you have given among these things? Param value 150 to 2400.
Sorry, param in the sense, yeah, that's number of parameters in the network, right? So I use a kernel of size 5, so which means 5 by 5. So a single kernel contains 25 learnable parameters. Then, and if my input image is contains a depth of 3, then a single kernel contains 5 by 5 by into 3, 25 elements. So it's just counting parameters, okay? And pooling layer, of course, you can reduce the ultimate purpose is that if I don't use pooling layer, then if I keep on using convolution layer, the size become deeper. That's what we want. But in 1990s, right, we don't have enough compute. But even today, if I increase the depth to 150, ResNet 50 and there are ResNet 150, if the depth of the network is 150 or something, then it is often advantageous to reduce the dimension of the input. Let's imagine I have an input size of 500 by 500. And I know that in image, most of the pixels are redundant, right? So by reducing the size, we are not losing much. I mean, in the same, by skipping few pixels, we are not losing much. And also it helps me reduce the size, right? So that's the reason why people use pooling layer. And of course, we can argue we could increase the stride value instead of reducing or using any pooling, because if you look at here, if I increase the stride value, it reduces the dimension drastically.
Yes.
But these are all design choices.
Okay, so even if we don't have pooling layers, if we just have convolution layers, and if we have enough computing power, you can just carry on, right?
Yeah. Pooling layer is an optional layer.
Thank you.
Yeah. Okay. So now I hope you understand the basic structure of convolutional neural network and some terminologies related to this convolutional neural network. So this is enough to write a code, and this is enough to understand convnets used for classification problem. Of course, when you go for segmentation problem, then there are other type of convolution, because segmentation involves, the input is an image, the output is also an image. In classification, the input is an image, the output is number of classes. Okay, so we have to do this, upsampling. Here you can think of this as downsampling. The output sizes keep on decreasing, but in segmentation we have to do upsampling. So people use something called as transposed convolution. But based on the problem you're dealing with, if you go to refer to some article, I hope you will be in a better position to understand all of these terminologies so that you can, write a code. It's not
I
going
think
to
unit does the job.
Yeah. The example is the unit, yes.
Sir, is segmentation similar to clustering?
Similar in the sense, you can use clustering for segmentation problem, because you're grouping, pixels related to a particular object. So you can use clusters, you can use probabilistic graphical models. So segmentation is kind of clustering, but now we are doing this through a supervised learning setup.
Okay, thank you.
Yeah.
So, sir, like you may differ this. Okay, in this recently, whatever these large models are coming, right? Like in that diagram, that convnet diagram, right? Where now this is a traditional diagram where you are giving an input and the output, and you are defining an objective function, and you are minimizing that objective function, learning the kernels, right?
Yes.
Now, recently, what they are starting, instead of giving a label data, like there you are using a reinforcement learning, right? For this PALM2 and BARD, all those models. BARD is a language model, but PALM2 is a vision model.
Yeah.
Correct. So can you show a schematic diagram how that look like? Because I'm getting hard time to even visualize that.
Yeah, I haven't even explored this PALM to all those things. So even in large language model, they use reinforcement learning as a feedback in the human loop.
How this diagram will look like for that?
No, how do you draw the diagram? Because that's really a big network, right? So there, see, in everything, right? If I understand about a single neuron, I could understand the entire multi-layer perceptron. If I know what is really happening in a single neuron, then I can understand what is really happening in the entire network. So I don't need to imagine that. Similarly, if I understand what a single convolution operation does, what a single kernel is learning, then when you scale it up, I don't really bother how do you stack it up, but I just know what really happens inside this convolution layer. The same thing goes there. There they use something called as transformer architecture. If you understand the transformer architecture, the one component of the transformer architecture where they call self-attention, then you don't really need to draw the entire diagram. People say I use encoder layer with some 24 or 70 encoder layers. That's all. That is enough.
Yeah, that is the embedding part, right? Like transformer, that is the embedding part. Now
not just embedding, the entire learning is that encoder layers.
Yeah, but like that feedback mechanism, like how not sure like how RL comes into the picture. Like if you have a like schematic diagram, it's also good.
Yeah, so I know it, but I mean, I know it conceptually, not in detail, but I think it's not the right place to discuss that as well.
Okay, sir. Okay, no problem.
Okay, now I'm just going to use the code that I already shared with you. Okay, so I hope you all have this link. Anyhow, I'm sharing this link once again. And I'm not going to run it because running it takes a lot of time, and you can run it your own end. Okay. So yeah, so scroll down and just click on this image classification collab. It will lead you to this collab notebook. Okay, so you make a copy of it and just connect. By default, it connects to GPU, but ensure that it connects to GPU because even in GPU, it takes a lot of time to train the model. Okay. So you are able to, I'm switching the tab. Are you able to see I'm switching back and forth?
Yes, sir.
Okay. Okay, so here, what is the difference? So previously I imported the Torch library, but now I'm just checking. Typically, when we train deep learning models, we always use GPU if it is available. Okay. And making use of GPU is quite straightforward. You don't need to know the internals and all these things about GPUs. You just make use of these functionalities. And of course, if you have more than one GPUs, then it is quite involved. We have to take care of all those things. It's kind of distributed computing, but in Colab, I think they offer only one GPU. Okay. So you just execute and ensure you are connected to the GPU, and it says what is the GPU use. Okay, all this available memory. And we are going to move a data from CPU to GPU. So I'm setting it.
How do we connect to GPU in Colab?
Yeah, that's a good question. I forgot to show. So you click runtime, okay, and then there you go and change runtime type. So since this Colab by default uses GPU, if you make a copy, then you end up using GPU. If you want to move to TPU, then you can. If you click none, it becomes CPU. If you have paid account, of course, you have an option to use some big GPUs.
So we should use TPU or GPU?
GPU. I haven't run the notebook on TPU, but it is safe to run. For the learning phase, you can run only GPU. Okay, so this are just I'm using. Later, I'm going to push the data on the model to GPU. So I'm setting it to CUDA 0. So 0 simply says I have only, it's an identity of the GPU. So we have only one, so we can ignore that. Okay. And all these models, right, we used in the earlier session. So torch.nn is the engine of entire Pytorch. So whatever the network you want to create, you have to use torch.nn. And this optim, if you want, we have to use an optimization algorithm. So this is actually contained in this module. Okay. And then Torch Vision, we already discussed all these things, data loader, transforms. Then I'm just downloading the data. And you can see, once again, we are doing this 2 tensor and normalization, all this. Okay. So remember, now we are not going to access these samples one by one manually. So we are going to make use of this data loader. the data loader actually makes things simple. So you need to just pass the training set, and of course, the training set must be in certain type. It's not just raw images. It has to be, Pytorch data set. There is a special class that is called as data set. Once again, if you really want to know all the details of this, each and every details of this Colab notebook, you should have, gone through all these tensors and AutoGrad Colab, and especially the NN module Colab, where we discuss all these details. So data set is the expected data format, okay, or data type that you need to pass into data loader. Okay, so everything will run smoothly if you run this, execute this Colab. But if you want to modify something, you should have at least you should have at least gone through this Colab notebooks and have some higher level info. Okay. Okay, so we have this batch size set to 4. Yeah, so all these things we already discussed, right? Now comes the connet, and remember, all these layers are already defined. So linear is the layer where we use this simple linear equation wx plus b, right? In the case of multi-layer perceptron, it is wx plus b. It is always the case. If it is linear, it is wx plus b, right? Now we are going to use con2d because it's 2-dimensional convolution. 1-dimensional convolution is also that. Typically, it is used in speech processing. Also, in few years ago, before the introduction of transformer, con1d is most often used in NLP as well. Okay. So you look at the parameters that we need to pass in to this function. It is in channel is simply what is the number of channels in my input. Okay, it's not just input to the first convolution layer, it is input to any convolution layer. Okay, they call it as channels. I called it as depth. Some people call it as blob, volume, whatever, but here it is called in channels, input channel, right? So for the first convolution layer, my in channel is going to be 3. Because if I use color image, my in channels is going to be 3. But for the next convolution layer, I mean second convolution layer, the in channel value is going to be, the number of filters I used in the first convolution layer. Okay, so I hope you are able to connect all these things. And out channel is going to be number of filters, right? Because each filter is going to produce one feature map. So if I use out channels equal to 10, it implies that I have to use 10 kernels. Okay, then the kernel size, you can define it. It could be, 3 or 5 or 7 or 11, whatever. Again, stride, you can define it. Okay, by default, it is set to 1, but you can define the stride value as well. And padding, for that is also optional. If you want to, ensure that the input dimension and output dimension should be same, then you have to do this appropriate padding. And the rest of the parameters, you need not to, bother about this for the time being. A bias is as usual. For each kernel, we add one bias. And similarly, we have maxpool 2D. And remember, maxpool 2D doesn't have any parameters, learnable parameters. It just acts as, reducing the spatial dimension. Okay. And all these things, kernel size, everything remains same. So now I have a necessary ingredients. Then I have to make use of these layers to create the network. Now I am creating the network, my simple toy connet. So as usual, the entire thing remains same. I have to inherit this NN.module. Okay. Then you name it whatever you want. And then you have to use the super class as. And this is my first convolution layer. Maybe I can zoom in a bit. Okay, so what is the first input? So first parameter is 3, because my input image is going to contain 3 channels because I'm using color image. Remember, I didn't mention the spatial dimensions. I don't need to. Okay, it could be inferred from the input data. And output channels equal to 6, meaning that I'm going to use 6 kernels. So each kernel produce one feature map. So output are stacked on top of each other. So the output volume is going to be 6. Okay, and the kernel size I'm using 5. Okay, and I'm defining the pooling layer. Okay, max pooling layer, the size is 2, stride is 2, and the kernel size is also 2. So I'm just repeating this. Con2D is, I mean, this is second convolution layer, and I know the input is 6 because the output from the first convolution layer contains 6 channels. So the input to the second convolution layer is 6. Then I'm setting it as 16, meaning that I'm going to use 16 kernels in the second convolution layer. Okay, same thing. So finally, we have this linear layer, which means I just use 2 convolution layers and 2 max pooling layers. Remember, I haven't defined another max pooling layer because the operation remains same, but here I used the max pooling layer twice. Okay. So now we have all the necessary, convolution blocks which extract the features. Then I have to use a typical fully connected neural network. So for that, we have to first flatten this out. So to flatten this out, once if I flatten that out, the spatial dimension is I calculated this. So going to be 5 by 5 and the depth is 16. So I just flatten this out. So the vector size will be 16 into 5 into 5. And I want to use 120 neurons in the first hidden layer. Then 84 neurons in the second hidden layer and 10 neurons in the output layer. Okay. So once again, notice that in the constructor method or in the init method, we have defined all the learnable parameters, or we define all the layers. The layer contains the learnable parameters. Of course, max pooling is not, in fact, it's not learning anything, but again, to stick with the, what is the norm, we are defining the max pooling layer there as well. Okay. And in the forward plus, we use this activation.
One question, sir, in the definition. Yeah. So in the FC1, right, the 516 is coming because of the convolution layer 16 kernels, right?
Yes.
And 5 by 5 is coming from the original size.
5 by 5 is this spatial dimension of convolution layer 2. The output from the convolution layer 2 will be 5 by 5 by 16. So if you calculate all these dimensions, right, I manually calculated this. Okay, it is not inferred. So if you use that formula, right, I have shown you.
Got it. Okay. So fine.
Yeah. So yeah. So in the forward, we have to define this forward method, and then there we are simply take the input, pass through the conv layer, pass through the activation function, and then pass through the pooling layer. Then you take the input. Remember, we are using a same input variable. It doesn't matter because internally it construct the computational graph, so it will take care of all these individual stuffs. Okay, it keep tracks of all the parameters that require gradients. Okay, so this is a convolution layer 2, same thing, and flattening thing is done by view. Okay, so view is similar to, you can use dot flatten as well, but view is often used because I don't want to make any copy out of it. Okay, so this is, even if you use flatten layer, that is fine. If you use dot flatten, that is also fine. Okay, and of course, now this is fully connected layer. We pass the flattened output to hidden layer 1, and then I use the ReLU. Again, output from the ReLU is passed to hidden layer 2. Once again, ReLU. Then now it is passed to hidden layer 3. Once again, I haven't defined any softmax stuff because I'm going to use cross entropy loss, which internally computes all these softmax and computes the final loss. Okay. Okay, now we define the network. It's very simple. So if you want to, make use of the convnets that already exist, right? So you can, people have already trained it and uploaded it. So Torch Vision contains almost all the implementation of all different implementations of different convnet architectures. So you can, if you want to just use the skeleton, the structure alone, you can load it. If you want to use the entire network with the pre-trained waste, you can use it. Okay, oftentimes, unless it is explicitly required, we never create the network on our own. Okay, all the layers are already predefined, so you can simply create them quickly. Okay, now as usual, we instantiate the class and assign it to some instance. And only difference is now I am moving it to a GPU. Okay, I created the skeleton, the structure. Now when I say skeleton, it's a computational graph. Okay, so I move that computational graph to GPU. So for that, I'm calling this tool. And then we simply print the model to see, this is what we are actually expecting. This no difference from the previous thing. I'm defining the cross entropy loss. Of course, I used the word criterion, but loss is also fine. And then we are using stochastic gradient descent, that is momentum based stochastic gradient descent. And it's a momentum parameter, you can ignore it. You need not to pay attention to it. Okay. Yeah. So now if you look at here, the entire training procedure remains same. No, these are all just additional steps I have written to compute the accuracy and loss. Okay. The only difference is that now since I moved the model to GPU, I have to also move my input to the GPU. Okay. And also I'm not accessing the samples manually one at a time. I'm just using this train loader, which internally uses, this data loader function. So when I call that, it gives me 4 samples because my batch size is 4. Each time I receive 4 samples with labels. So when I assign this data to this, it actually gives input contains 4 images and their respective labels. If you have set batch size equal to 32, then these inputs will contain 32 images. Okay, that's simply a batch size. So I don't really need to bother about how to load samples batches, right? So that's what data loader exactly does. And the primary purpose of data loader is manifold. It is not just doing this batch, especially when you deal with multiple GPUs. Sharing the data is not trivial task. Okay, taking care of and sharing the data across multiple GPUs and getting the gradients from each GPU and accumulate them is not so easy. So that's where data loader actually pitches in. So if you look at the documentation of data loader, you see about 20 plus optional arguments, okay, to take control of sharing the data across multiple GPUs. Okay, now everything remains same, 0 grad and getting an output from the model and passing the outputs and the true labels, compute the loss and compute the gradients and update the parameter. Now you repeat this. Okay, so now we are not actually using stochastic gradient descent. Now we are using batch gradient descent because we are sending the samples in batches, right? And then this is just our way of computing the loss and accuracy. Of course, you could use sklearn metric, but long ago I used my own, so I just retained as it. Okay. Then if you run it, you can see, getting 50% accuracy in CIFAR is quick, but getting 70 or 80 is not that much straightforward. 84, you have to run the notebook for days, okay, just to get accuracy of 65 or 70.
Sir, I ran the training like 3 or 4 times and now I am at 68%.
Yeah. So I hope I am loading all the samples. I'm not running. Yes, I'm loading all the 50,000 samples. So if you are running it in GPU, you can run it quickly.
It's taking up 1 minute.
1 minute for?
To run this code.
Okay. For this entire 2 epochs. So I think in this 2000 actually implies 2000 into 4, which is we are passing 8,000 samples and updating the parameter. So it makes sense. 12,000 into 4, 48,000. So yeah. So you are getting 68% accuracy. That's great. So that's training accuracy, right? So still we need to evaluate for testing. Yeah. So here is a thing. So once you train the model, you want to, either use the model for inference or to, measure the test. So no training is involved during these 2 steps. So we have to put the model in evaluation mode. The reason is that otherwise the model construct the computational graph for each input if you pass the test sample. So I have to get rid of the computational graph. I have to retain the weights, trained or learned weights. So we have to put the model in evaluation mode. Okay. And then you can pass the test samples, move the samples to GPU, and then compute all this. Fortunately, it is 54. I don't know what is the test accuracy at your end.
63.
Oh, that's really good. Okay. Okay, so now you know how to put the model in evaluation mode and test it. And of course, you can use this for inference as well. If you can put this into Streamlit if you want. Okay, you can somehow build an app for using ConvNet for any image classification task. And oftentimes we don't want to train the model from the scratch, especially if the model is really big, right? In the case of AlexNet and ResNet, what we can do is that either we can fine tune it for our task, okay, that we call it as transfer learning, or we can use as is, okay, without doing any modification. So Torch Vision supports that as well. So here in Torch Vision, I'm just loading models, and it contains so many models, okay, even it's a dense net, which is if you're some models have only maybe some millions of parameters, but other models might have some 50 million, 60 million parameters. So whatever the ConvNets you study, okay, you come across the literature, most likely you found that model in the find that model in this Torch Vision, okay, because they also keep updating their repo with all these models. Okay, so if you decide the models you want to use, then the rest of the steps remain same. Whatever the model you want to use, you call it, then you pass this argument pre-trains equal to true. What it does is it loads typically we randomly initialize the network, right? But when I set pre-trains equal to true, it creates the architecture and the parameters are set to whatever that is trained on that architecture, right? So after training, then we learn some parameters. So those learned parameters will be loaded when you set this pre-trains equal to true. And I want to use as is. Now you can see we are doing some transformations, not just to tensor. Whatever my input image, I first have to resize it to 256, and then they do something called as center cropping, and then usually convert that into tensor, all these steps. You can now see mean values are different and standard deviation is different for different channels. Okay, this we need to get it from whoever created the data set. Okay, hopefully this information will also be available. So it's now straightforward. You can see, right? AlexNet, again, they define this model using Torch NN.module. You can write all these things manually, or you can use them as is. Okay. Now I just randomly load some image from internet, and then this is a goldfish. I pass it through AlexNet, and it says, I think somewhere, yeah, it's a jellyfish with a probability score of 80 or confidence score, right? But I know it's not jellyfish. So let's see the performance of ResNet. We can simply switch to ResNet as if we are switching. It's a straightforward process, right? So I just load ResNet 101, which contains 101 layers. A small version is also there, ResNet 50. Then I'm just passing the same image through that ResNet, and it says it's a goldfish with 99.9 accuracy. Okay, because AlexNet is the is the one that triggered this entire deep learning booming. So then people came up with different types of architectures that outperforms the previous architectures. Okay, of course, at the cost of increasing the number of layers. Yeah, this is, you can use pre-trained model as is if you want to use it. But if you want to fine tune it, there is another setup that is called transfer learning. But in the Pytorch documentation, now if you go through it, you should be in a position to understand this entire code. Okay, so in transfer learning, what we do is, while we load the model, right, I am setting pre-trains equal to true, and then I use the entire architecture as is. But in transfer learning, what we do is we change the final, maybe few final layers, fully connected layers. The output layer has to be changed, because in the previous case for AlexNet, ResNet, all of them are trained on ImageNet. Therefore, the output layer contains 1000 neurons because there are 1000 classes. But for my problem, if I have only 2 classes, then I have to replace the output layer. And also oftentimes people replace because you want to fine tune it, right? So oftentimes replace few fully connected layers, okay? That you can access these layers by using this model, okay? The same thing, now I'm using .fc in futures, and I can add my own layer like people do, like, right? I can simply replace it with, you can use nn.sequential, things like that. You can simply add your layers if you want, and then you can fine tune the entire model or only few layers of the model. Okay, that is transfer learning. But hopefully the documentation now helps you to do different things, because the entire coding remains same. You should be now able to understand all these stuffs. Okay.
So one question, you said, for ResNet, you use the pre-trained, right? Which means the previous training that we did, is that what we are using, or are we using ResNet's pre-trained?
No. Pre-trained is the term that we use, if I want to use a model that is trained on one task for a related task. Okay. So let's say I train a model for image classification where I want to recognize whether the image is cat and dog. I train the model and it performs really well. Now I have another task where I want to recognize whether the image contains, let's say, a deer or a lion. Okay. So these two are related. So what I can do is, instead of creating my own model and training it from scratch, I use the existing model, okay, which is performing well on the related task. I take it and then I just fine tune it. Instead of randomly initializing the weights, I just use the weights as is, and then I fine tune it. That's what we say it's pre-trained.
So can you just show the steps above this, just when you start the ResNet? Okay. No, this is the, okay. Okay, I think I'll look at the collab and then probably ask you later.
This one, right?
Yeah.
Yeah, pre-trained means, see, AlexNet is a ConvNet, right? I have some convolution layer, fully connected layer, all these things. Now I have parameters. So if I set pre-trained is equal to false, it loads the AlexNet architecture. Then I have to randomly initialize the weights, and then I have to learn it by passing my data. But when I set pre-trained is equal to true, instead of randomly initializing my weight, it takes the weight, how do I say it?
So this is from the defined model itself. That way, if I do it and you do it, we will get the same weights, initial weights.
Yes, that's right. Yes. From a trained model. So the weight initialization differs. That's the difference between pre-trained. Okay,
sir, can you revise the AlexNet like completely again?
You mean AlexNet architecture?
No, the codes you wrote.
Okay,
the codes. Yes.
Okay, here. So the architecture, I think you can make sense of it right now. Con 2D, all these things. Kernel size is 1111. So now we have an architecture. So here what I'm doing is I'm just getting data from net. Okay, so this is something, we use some external packages, and of course I have to figure this all out by trial and error. But here I'm using byte ISO. Even I don't know why I use bytes IO, right? So when I created all this, I may have encountered some errors, then I fixed it. So the intention is to get an image from internet. So I have to ensure that it is in a proper format. Now I have an image in a proper format, right? And if you look at the original image size, it is actually 1000 by some 700 or something, or 700 by 1000 something. Okay. And you can see there are some watermarks, all these things, but the AlexNet model was in fact trained on images of size 226 by 226. Okay. So if you go here, 256 by 256. So no matter what my input image size is, okay, of course I have to ensure that the size is not less than 256, but if it is greater than 256, I can use this free size. Okay. So what really happens is that when I feed in an input, it goes through this transformation first. Okay, first it converts my input image size into 256 by 256, and then do this center cropping, and then this image is in NumPy format, I believe, and then it converts that into tensor. Either I think 2 tensor can work if my input is either NumPy or 2 image format. Okay. Okay. Yeah, so I'm calling this transform explicitly. I don't know why is that.
Karthik, can you?
There are many people. Yeah, I muted them. Okay, so here I'm passing image to this transformation first. Okay, I have to make the input suitable so that I can pass it through the model. Okay, then I use this unsqueeze because when you train the model, right, you ensure that the model contains an additional dimension as well. Okay, it is always when you pass the model, it is not just 32 by 32 by 3 in the case of CIFAR. During inference, I have to also add one more dimension. Okay, because the one more dimension is the batch size. So here the batch size is 1 by 32 by 32 by 3. Okay, so for that we are using torch.unsqueeze, which means it adds additional dimension at 0th dim. Okay, then that's why I call this as batch. Then I put the AlexNet in the evaluation mode. I'm not going to fine tune it. Okay, I'm not fine tune on my new data set. I'm just going to use it as is. Okay, I feed in an input, get the probabilities for all the classes, take the argmax from it. Okay, so I'm passing batch as an input to the AlexNet. Then I get a prediction. Then prediction, this is 1000 class classification problem. So the prediction is of size 1 by 1000. Okay, and I want the name of the classes. So I can't type all the classes, and also I don't know the order. The 0th class, when it was trained, the 0th class could be something, right? It's based on either the dataset, whoever created the dataset might have that order, or whoever trained the model might have followed some order. So we have to take that order. Okay, so that I just loaded from the Git, which I have come across. So I'll use that. And then, this is just to come up with this final class names. So the max is, now why am I doing this? I should have done argmax. Max of pred, 1. Why I done that? The prediction contains the probability for all the classes. Torch.max actually retains. Okay, so max actually retains the probability value. Okay, argmax retains the index. Okay, so there are two. So you just take a look at into torch.max whether it returns the probability value as well as the index that I have to look at. Okay, so hopefully the thing is I have 1000 numbers. So I want to look at which class the maximum number belongs to, and also the value of the maximum number, the probability value. Okay, so that's what we do here. And why am I doing this softmax stuff here is, this model is also trained on cross entropy loss. In Pytorch, when you use cross entropy, we have only that, logits, right? The cross entropy internally uses the softmax. But during evaluation mode, if I want the probability score, I have to use this softmax function explicitly. Okay, so I pass this prediction through this softmax function. Okay, just to get the probability score. So it is 0.8 and we are just displaying it. But the argmax should return the same value whether you use this on pred or on the output of this percentage. Argmax won't change, right? If you have any question.
No, sir. Got it. Sir, one thing that I able to find as a newbie, sir, in deep learning kind of stuff, many things are based on hit and trial type of things. Like,
yeah, it's a trial and error because there are many things that we really don't know. So it's an empirical thing. So we have to an experiment is, but it is not that random. Okay, so when we say trial and error, it's not. When you make a decision, you have to ask this question: why do you think it is useful? Okay, out of all the possibilities, what do you think? Say, even if when you choose an activation function, if someone says ReLU is best, then the immediate question will be, why don't other activation function? Why do you think ReLU is good? So there must be some questions on all your decisions. And if there is no concrete answer for that, then we go with trial and error. But if there are some intuitive explanation, most often the explanation revolves around the concept of gradients. People look at how the gradient flows in the network, whether the gradient flows across the network or it is blocked. So even if I use ReLU, all these activation function, if I am not able to pass the gradient from the output layer to the input layer, then there is something happening inside the network that we are not aware of. So that's why people come up with residual connection. They capture this, then they come up with an idea that let's create a residual connection and see how it works. Okay, so yes, it is trial and error, but sometimes we have to make some educated guesses, decisions.
got it, sir.
Okay, so I'm pasting the attendance link in the chat. I hope you have 45 minutes to mark your attendance. Okay. Okay, so that's all from me. So all the best. And of course, I am not able to cover RNN for various reasons. RNN is quite involved than this simple image thing. But once again, if you are curious, you look at this, and there are plenty of articles out there, which explains RNN in great detail. But now it is transformers, it's no longer RNN. So go and learn RNN only if you are sure. You have to use RNN, other than that, you have no other choice. But if you are using some NLP based application, try to learn transformers because they are best. So learn transformers and try to use them. Okay.
Sir, I have one more question. During the coding time, like during we are doing practically writing codes, there are many places where every codes or like every function we call we cannot able to remember, or like it is also on debug basis, sir.
Yes. No, I'm not sorry, I'm not able to get your question. So many functions remember in the sense during the exam.
No, actually writing some codes, like if I wish to train some CNN, and so does it necessary to follow, like have the same code, or like?
Oh, you are asking some structuring your project. How do you structure your product? Same code in the sense, see.
Yes, sir, structuring about.
Okay, structuring a project, yeah, we have to follow a standard practice. There is no, hard rule. It is somehow related with software engineering. So when you build a project, right, you want to modularize it as much as possible. It's not just writing the code, and you want to model. So you segregate the different thing. It is like when you train a model, we keep data separate, and then we keep the models separate, and we keep the optimizers separate. Okay. And then we keep the testing stuff separate, right? We maintain a separate script. So the standard practice is your model skeleton goes in one script, because if your model is really big, right, you can't write everything in a single script. So the better thing is you move those models and things to a separate script and maintain a configuration file, right? So most often, if you want to, release your work as a package to someone else, so it is always better to maintain some configuration file. So by just editing the configuration file, some developers should be in a position to make use of your code. So it is about modularization. We have to follow this software engineering practice. And of course, if you refer to some standard GitHub repo, you come to know how they organize the code and you follow the same. Most often, that should be a good practice.
Sir, what are the direction of research happening in this place, this space?
The direction is 360 degree. So it's very difficult to keep track of the direction. Because
no, basically, yeah, the reason behind asking this question is, one thing is like whatever has happened in past, right? So there are multiple like layers. See, if we take from lineate to your like all these like various coordinates, right?
Yeah.
Your LXNet and all these things, like slowly they are increasing the number of filters.
Yes.
Number of layers. Point number one. Number of different using multiple filters, and then maybe like steep connections, right? So these are the three different strategies that has been followed in the research. So any new thing like that is happening in the recent trend in this space other than these three?
Yeah, so now people are exploring transformers. Okay, so now they even try to bring in this transformer to computer vision domain, because transformer seems to generalize well. Okay, in the sense it learns the language quickly. Therefore, they try to learn instead. The label, image and label thing is really a costlier stuff. So for each problem, I have to collect the images and the labels specific to the problem. And then if there are pre-trained models, of course, I can use it. But in the case of language, right, so the entire ChatGPT or whatever is actually trained on unlabeled data set. Okay, the entire collection of Wikipedia, all these things. So it learns the language at its core. But when you adapt it to a particular NLP problem, it quickly runs. You don't need to collect a lot of training samples and labels. Same thing they are trying to do in computer vision domain, whether it understand the image, okay, but it's very difficult, but they are putting in effort. Now, as far as I know, the research direction is along how do we adapt transformer into computer vision domain. It's really interesting. First, NLP actually tried to adapt concept from computer vision to NLP domain. So there comes transformer. Now people are trying to adapt transformer into computer vision after seeing their performance.
Okay, so like that is kind of a like going from supervised to semi-supervised kind of learning, right?
It's not semi-supervised, it's completely unsupervised.
Completely unsupervised.
Yeah.
Okay.
Sir, I have a question. Right in the beginning, sir, you had mentioned that typically deep learning works well for unstructured data, right? And not so much for structured data. So I just wanted to clarify, did you say that because for structured data, or let's say tabular data, and you have very clear features and all of it, is it an overkill to use a deep learning model? Is that why you're saying it? Or because I don't see why a neural network should be inefficient for tabular data. It may be like you're using a too big a tool to solve a small problem. That could be the case. I just wanted to clarify that.
Yeah, so I don't know the actual reason why, what is the lag behind this neural, why it is. I have gone through some articles. Okay, so the centered claim is that no matter how much they try with deep learning, XGBoost always outperforms. It is not able to outperform XGBoost. So I haven't gone to the under the hook why it is doing so, but I know that still deep learning is not suitable for tabular data.
Okay. So it's not able to outperform. So basically, we are using something which is like very expensive or very unwieldy to solve a problem which can be solved with something which is much simpler.
Yeah. So the information is highly organized. So decision tree generally, make use of those informations and come up with the best kind of decision boundaries. And of course, XGBoost, all these things are just kind of extension. But I think there is a research why neural network or how we adapt neural network for this tabular structure. Can we come up with different architecture? So in that aspect.
Yeah. No, I am completely convinced with what you've said, in the sense that I am a big fan of Occam's razor, which is if you can make do with something which is simpler, then use that. Why use a complicated solution? The other thing I wanted to mention, this is more a philosophical kind of point, which is which just let me know if I'm correct. See, in the problem with neural networks is whenever you have a certain, whatever problem you're trying to solve, if you want diagnostic information, right? For example, let's say, one image is rated better by people versus another image. You can do that. Like you can identify which images people are liking versus the rest, or which image is better, higher quality versus the rest, or whatever that is, right? So, but why are people rating one image better than the other? That a neural network can never give you. That's because it's a black box. We don't know how exactly that feature extraction is happening, right? So whenever you have a problem of that kind where the diagnostics are important, you need to know why something is happening, then you have to rely on traditional machine learning methods. Is that a correct way to think about it?
Yeah, that's partly correct, but I have gone through some books. I mean, I don't remember the name of the book, but see, one thing people do is that when this is in the setting of how do we recognize whether a face is just recognizing male or female, we do that by looking at the face. But if you ask someone, how do you recognize that? Even we have no clue, right? I'm just doing that. I can't pinpoint how am I recognize this is a male or this face is a female. So what they do is that they take a neural network and then train, and then they see how the neural network actually learns whether the face is a male or female, which part it actually focus the attention to. So by studying that, they came to know about that it is about the distance between the nose and the lips. Okay. So it looks at structure of the nose and lips than the rest. So to verify that, you can reconstruct the experiment. You bring in some audience, and then you change these nose and the lips distance, and see whether they are also struggling to recognize whether it's a male or female. Then you modify that, but they observe this pattern. So this is kind of coming up with
that's correct. No, that's very very informative, in the sense that basically they're able to pick up diagnostics. So is it easy to unpack like that? I mean, for a complex neural network, is it easy to do that? Or eventually people will figure out how to do it easily? Because a lot of times people prefer traditional machine learning models simply because if you have to explain the output, why is something happening? Let's say you're predicting, the stock prices, or you're predicting the GDP. Then you have to answer why are you saying GDP will go up or come down, right? You have to say something. You have to say that, okay, employment rates are lower, or currency exchange is bad, or imports have taken a hit, or whatever that is, right? You have to give some explanation. So whenever there are explanation, people avoid deep learning models. So do you foresee that in the future that problem will be overcome? Because the example you gave, essentially people are able to unpack what's happening in the neural network.
Yeah. So in fact, I think maybe I have mistakenly said that they have used the SVM classifier. I'm not sure whether they have used deep neural network, but it is long ago. I think the book was written famously, but I don't remember, but I share it if I come across it. Yeah, what you are saying is the explainability is the biggest bottleneck of deep learning, that unresolved problem of deep learning. They still deep learning is thought of as a black box. Even though you visualize all the kernels, but the final decision made by the deep learning architecture can't be justified. Okay, so that's the biggest problem. I think the research is still in its infancy. It's not that they have some idea now. We don't have any clue. So there is another branch of study called Bayesian deep learning. So everything is about the parameters. So they assume the parameters are drawn from some distribution, and then they condition on it, and then trying to apply Bayesian theorem on it. but I don't know how it is going to work at the end. But still, everything is in research.
Okay.
Practically,
Okay. Thank you.
the practical. Sorry.
Yeah.
In the continued question, practically the lack of explainability, right?
Yeah.
Is that a hindrance in using deep learning for some applications? Say I want to do it for medical diagnostics. So
it's not a hindrance in many applications, but it is extremely crucial for, let's say, for what is that? Defense applications, right? So if something has gone wrong, right, even if you want to use deep learning to control the airplane, right? So even then we might have come across news like the airplane went perpendicularly, it's a nose dives kind of stuff, right? So there, if you want to decode what went wrong, now it is possible. But if you leave the autopilot to deep learning, right? If it makes mistake, then making mistake is fine. But if you're not able to debug why it made a mistake, then that's really a critical failure, and it also costs lives. So in such a case, still, we can't use deep learning.
Yeah, so whenever there is a like regulatory compliance, so and legality.
Yeah.
Legality required. Say, for example, you reject a loan stuff, right? Loan application. So you need explanation there because that is the legal requirement.
Yeah.
And regulatory requirement. So for those applications, like you need to avoid, unless like AI has shown that maturity or you have that causal causal explainability. So legality, regularity, and regulatory stuff, and that where accountability comes into the picture.
Yeah, you're right. Yes. And in fact, that you can listen to pioneers from the deep learning, the podcast from the pioneers from like Jan LeCun, and there are many, right? So their debate is quite interesting. So even if you ask a decision made by a human, whether the reason given by the human is justifiable or logical. So if you ask those questions, even we make decisions, right, with some intuitions, right? We don't have some logical conclusion, but yet we make a decision. So in that aspect, we can't expect deep learning algorithms are kind of similar, like reproducing the human, not exactly the human intelligence, but at some, on. So it's still a philosophical questions, and there are people arguing for and against it. Okay, so there is a lot of hope then. If there are confusions, then there are scopes.
Yeah, but it has a lot of scope in the drug interaction and drug designing and new material search.
Yeah.
At least it will give a probe, like from a infinite database to give some idea that okay, where research can happen. Narrow down the problem to some extent.
Yeah. Okay, so I hope you all have marked the attendance. So I have forwarded those who have missed to mark the attendance in the last 2 sessions. I just forward the details. I hope I can, we can manually override that, but let's see. And thanks for joining the session. Glad to have
Excuse
this session.
me, sir.
Yeah.
Yes, sir. Thank you, sir. Can we leave, sir?
Yeah. The rest can leave.
Thank you.
One last.
So I was actually asking about
one last request. Sorry, I'll just take 10 seconds. Sir, is it possible for you to share those slides which you have shown us?
Yeah, definitely. So it's from Professor Desktop.
As a PDF or something like that, sir, is it possible?
You mean the slide I used in the previous sessions?
Yeah, all 3 sessions.
Yeah, sure. So today I used the slide from Mitesh Kaprashar. I can share it. There I have to convert that into PDF. I share it. Yes, of course.
Yeah, because I tried to do it online, I couldn't. So if you can do that and share it with us, it will be immensely helpful. And
sure.
And thank you so much. Wonderful sessions. I mean, I've not followed most of it, but I've learned the philosophical underpinning. So thank you very much.
Yeah, thanks a lot. Thanks. It's nice to hear.
Excuse me, sir.
Thank you, sir.
Thank you so much for the 3-day session, sir. Like, I'm the beginner, so I mean, you started from the basic level and moved on to the complex level. So it was really helpful for a beginner like us to understand what exactly the concepts are. Because without knowing the concept, if we go to coding it, I mean, we couldn't. I will be in the like in the middle of the forest. So it was really helpful that you started from the basic and then moved on to the complex level. And we learned many new things actually. So to be frank from this workshop, and we need to actually explore more to understand more of that. But within the limited time, you have really explained very well. You have covered all the levels of people. So that was really great. So thank you so much for the 3 days.
I totally second what he said. Totally second, because one, while I've done MLT and all, obviously there's a lot more to do, and that, and second, we also understood there is so much more to learn and what all needs to be learned, right?
Exactly.
So thank you very much.
It's like, it's not stopping with what algorithms we learn in the courses. It's like,
not even,
it's like even we have to do a research kind of a thing. It's like
that is going to be true. See, even if you come into deep learning, right? Even I still feel now, if you look at the research direction, how fast it progress, I sometimes often feel I'm lagging behind.
It should be done like a research study only, because I mean, it has started like a dot, but it is going somewhere. Like, you need to understand more complex concepts. And I'm also a beginner with Python coding, so have to understand the coding parts as well. So that will take time.
Thank you so much. Thanks everyone.
Thank you so much, sir.
Thank you so much. Another question. So are you involved in the deep learning course, degree level?
He's the instructor for it.
Yes, I am the instructor for the deep learning course.
Oh, great.
So I'm conducting this session to attract all you people to deep learning. But
I've already registered, so we have to do deep learning anyway. So it's a mandatory course. But I'm doing it this term. I mean, in the May to September term. So hope to see you in the live sessions.
Sure.
Sir, is there a like scope for the BA students to get kind of get associated with like kind of work that you do, or some kind of a research under some professor? Like, is there a possibilities or something that sort of?
You can do internship, but I think for that you should have completed deep learning. So if you want to tackle problem related, or with deep learning models, you must have completed deep learning course. Some students are working with us, but if you want to come to on campus, and then I think we need to discuss with the prof. There are some areas where we in fact let the students work on. So if you satisfy that criteria, then you can work on it.
Okay, so like for that completion of the degree is mandatory, or what?
No, you have to satisfy the prerequisite, right? So if you want to work in deep learning, then having a knowledge in deep learning models and also experience in Pytorch is helpful, right?
Yeah, so I have like worked on this deep learning stuff extensively along with Pytorch and TensorFlow and all those things. Okay. In fact, like some work on that few-shot learning, zero-shot learning, all those things. Okay, but if we need to say, for example, extend that further, as I asked you one of the question, right? Because recently in Google I/O, what I learned that what you said, right? Like you can interrupt, you can feedback with prompt, like another image, right? Another image. So the way your ChatGPT works, similar kind of thing, POM2 will work. Like you give them an image and then tell that, okay, this image you generate something very close to this. Okay, so this kind of thing. So that is the work that has been done recently in Google. So that was the reason I asked, like, what is the future direction where this research is going on? But like, is there a way that we can get associated and do some work currently and all these things? So that's the reason rationale behind asking this question.
I understand. But those kind of research, we are not doing that much level of research. I mean, they are trying to, as I mentioned in the beginning of the session, right? So one advantage of this deep learning algorithms is that they can work on all these 4 data types. So there is a possibility of, coming up with single architecture that could understand all these 4 modalities and, relate with them. So POM 2 is kind of doing that, right? So it understands text, images, and then videos. I mean, it means both generative and as well as discriminative AI, right? So I think people at Google and Meta and DeepMind, they are doing such kind of research. So if you really want to, do along that area, then that is the right place. In IIT, I think you might have heard of AI for Bharat. So they are tackling the problems related to, India.
Mm-hmm.
So it is like there are different roles of developing an application. And if you want to do research, of course, PhD is the only option. But to develop an application by using the existing models for, let's say, for local language, such kind of projects are there in AI for Bharat. So you can apply for it.
Okay.
Sir, research projects are like we have to be in IITM and is it like an on-site research projects or we can do it from our
research
places?
It is often residential program. So even if you want to do research, but again you must have completed PhD in order to involve in that. Not PhD, I think MS or ME.
Okay. So, no, actually, I've completed PG, but I've done MBA. This I've taken. My BE was in IT, but this I'm doing is. I had a career break, so to fill that, I'm doing. Just want to have a career transition doing this course. So just wanted to understand in case if we want to proceed further on this. So can we go on to research? So for that we need to be. That's what, as you said, it should be residential, right?
Yeah. So research level, I think only the residential programs, AI residential programs are there. But of course, no matter which background you are from, so if we have showcase what you have done, right? So that will definitely allow the people to, work with them.
Got it. Yes. Got it, sir. Thank you so much, sir.
Yeah.
Sir.
Thanks a lot.
Sir? Excuse me,
please
sir.
go ahead.
So actually, I missed yesterday's attendance. So is there any way to?
The only one way is to you give me your roll number, then I actually discuss with the ops team, and if they have some way, they can mark it. They can manually override.
Okay. So sir, where do I send this to you?
You put your roll number in the chat. I make note of it.
In the chat. Okay.
Sir, even I missed yesterday's attendance. So shall I also put my roll number?
Yeah, please put your roll number.
Sir, I would like to implement this deep learning in some NLP related tasks. You have mentioned the transformer is the best tool for do the NLP related. Yeah.
Yes.
So, can you please throw some lights on that point? Because this is the first thing I am learning about deep learning and all those things from this workshop only. So currently I'm doing that NLP related task using some traditional programming, Python programming only, but I am interested to implement this deep learning in that task. So is there any good suggestion?
If you want to do problems like, let's say, NLP problems like classification, sentiment classification, or question answering, or summarization, so these are all really high level tasks. Okay, even name and entity recognition, these are all high level tasks. So for tasks like these, you can apply deep learning, especially let's say you want to classify, given a big paragraph or given a big document, you want to say whether it is a positive or some classification, but the document size is, so in that case transformers works perfectly. But if you want to classify a small document or a small paragraph, right, with few sentences, and if there are some memory constraints, constraints like this, then going with RNN is fine. But once again, people almost completely abandoned RNN. They go with transformer, even a small transformers. So I would, nowadays it is kind of advice like you start with transformer and see how it works, and then if it is not, of course the performance should be on par with RNN. There are some problems with RNN in the sense training the model is difficult and you can't expect the RNN to work on really big documents. Okay, it won't really work well. So in that case, they switch to transformers. So the general idea is that if you have NLP problem, start with transformers and see how it works. Even Hugging Face, which a common platform which offers many models for various tasks, uses transformers only. If I'm not wrong, I don't know. I haven't seen any RNN based structures there, but
yeah, the problem statement that I am currently solving is, let's say for your name, some cases someone it's written Prakash Arun, and some cases somebody write it's Arun Prakash. The task NLP task is to identify these names are similar. So it might be sound easy, but some other crucial cases, the pronunciations and all those things is my concern. So I'm doing it currently doing this by hard coding something and using some distance matrix, like calculating the similarities between two strings, something like that. So is there a way to implement this kind of deep learning in this field, in this kind of problem statement?
Yeah, I have seen problems related, similar problems, like given a name, you classify whether it is a male or female. So it differs based on the region, right? So you can't simply say by looking at the name whether, even for us, it is difficult whether it's a male or female, right? So for that, they use deep learning algorithms, but since the input is going to be very small text, right? It's not going to be big text. You are just going to give the name as an input and you encode the characters, and then you feed in those and it gives you an output. In such a case, you may try with RNN, not necessarily transformers, but it is possible. But how do you collect the training set? How do you represent, because Arun Prakash is most common. Prakash Arun could also be possible, but you have to, design the data set. You have to design how are you going to collect samples and how do you name the labels. So these are things you have to fix, but you can use a small deep learning models.
Yeah, okay. I have the data sets. Let me try it once. Yeah, thank you, sir. Thank you so much.
Yeah, sure. Thanks. Okay, thanks a lot. Is there any question? Yeah.
Sir, for the certification part, I'm getting to know from various sources that we have to submit some kind of proposal for a project or something.
No, I think that's for the workshop. For the students who have completed the deep learning course in this term, right? For them, they have to submit the project proposal, not for this.
Okay, so for this specific DL workshop, we don't have to submit any kind of project or any proposal.
No, that's not required for this workshop.
Okay, all right.
Yeah.
Thank you.
Yeah.
Sir, I had a question.
Yeah.
So for general image classification task, the normal classification decision trees and everything else would outperform DNNs, is it?
Sorry, for general image classification task?
Will the normal classification methods outperform DNNs, like decision trees and everything?
I'm not able to get the question. Can you put that in the chat so that I can understand that?
Yes, sir. Yes, sir.
Yeah. Okay, so object identification or image classification task, you are asking the face recognition. Okay, so we have to use CNN. You're asking for the model. If you're asking for the architecture for these problems, CNN is the go-to architecture. So now this word DNN, right? Deep neural network. When I say deep neural network, now we have a variety of architectures. Which one you are referring to? Whether it is a multi-layer perceptron or CNN or RNN. So DNN is kind of that's general term that refers to all deep learning architectures. Do DNN perform better than other ML? Yeah, so there are other ML classification like XGBoost that performs well in tabular dataset. So it is not always the case that DNN always outperforms all other ML algorithms. Yes, of course. Okay, I noted down all the attendance, so I try to mark them. Okay, thanks everyone. Now I'm dropping. See you again, maybe in the deep learning course.
Yeah, thanks, sir.
Thank you for the
Thank you
workshop,
so
sir.
much.
Thank
Yeah.
you.
We'll see you soon
you,
in
sir.
June. Thank you.
Yeah, sure. Okay, bye. Deep learning books, there are many. So if you want to just learn deep learning from the implementation perspective, or from a developer point of view, there are so many books out there. But to learn Pytorch, documentation is always the best choice. Of course, documentation in the sense the tutorials in detail, not going the individual functions. You can also refer to GitHub, just posting. Okay, so somehow I organized the content so that anyone who is starting with who want to develop deep learning model with a good understanding, they start with Tensor and then AutoGrad, which are two engine and fuel. Once you understand them clearly, then you can develop any model you want.
Yes, I will go through your GitHub anyways that you've shared entirely. But I was asking, like, I've started with Ian Goodfellow's deep learning book, as it's also referenced for the deep learning course. I think it's one of the reference books.
Yeah, Ian Goodfellow is quite involved. I mean, it involved in the sense, if you have some background in machine learning techniques, then it makes sense because the math remains same. It's too technical, and also it was not updated post 2018. But there are many architecture. But for the fundamental deep learning, of course, you can start with Ian Goodfellow. And Pytorch and
yes, sir.
Yeah, so for any deep learning framework, it keep evolving. So you always refer to, the recent release of any book. If you refer to a book released in 2018, right, about Pytorch, it is no longer there. So Pytorch evolved a lot.
Right. So for learning Pytorch, documentation is the best option.
Yeah, documentation or any book that are recently released.
So can you recommend something?
No, I haven't used any books for Pytorch. So I have gone with documentation because anyhow I have to stick with Pytorch. So I have to know the internals. So I've gone with documentation.
Oh, okay, sir. Thank you, sir. Thank you for the session, sir.
Yeah, thanks a lot.